Hello everyone. So today's topic will be amplitude modulation. But before that, we'll discuss the modulation process, the general modulation process, and different types of modulations we'll see. All right. Then we'll go for a discussion of amplitude modulation, and we'll derive or obtain the equation for AM. Okay. So let us start with the definition part of modulation. So modulation, as you can see, is this systematic alteration or changing of one waveform. Which waveform we are going to vary is this carrier waveform, high frequency carrier, right? So this is a high frequency carrier wave, and its characteristics, certain characteristics will be varied in according to the waveform, which is a low frequency message signal, right? So this is our message signal in here, right? And this we have already seen. This is the carrier signal, right? High frequency wave, and this one is low frequency wave, which we generally call as baseband signal. Okay, and these both signals are fed to the mixer, okay, or modulator, right? And the output will be one of out of these three, right? Actually, our main focus herein is analog modulation, right? So we'll not be considering the digital ones. So we'll be getting only analog outputs, right? So one is amplitude modulation, other one we have frequency modulation and phase modulation. In amplitude modulation, your frequency and phase remains the same, but the amplitude of this carrier is varied in accordance with amplitude of this signal. All right. For greater amplitudes, your amplitude of carrier will get increased, right? Basically, this amplitude of message signal will get added up to this amplitude, right? Likewise, for negative cycle of analog signal, your amplitude of carrier decreases by an amount equal to this, okay, and it will go on like this. Likewise, if we are performing frequency modulation, so your frequency will vary according to the amplitudes of your message signal. All right. For positive cycle, you'll have high frequency component, means the frequency of this carrier will increase, right? For negative cycle of message signal, frequency of carrier will decrease, okay. Likewise, whenever there is a zero crossing in here for your signal, right, you will observe a phase change in the output wave, okay, that is phase modulation. All right. Now, what is the goal of modulation? We have already seen why we need modulation, but main goal in one line, if we say, is to produce an information bearing modulated signal. This is your modulated signal, right? This side we have modulating signal. When these two gets mixed up, we'll get modulated signal. So this we have to produce this modulated signal, a modulated signal wave whose properties are best suited for efficient utilization of communication channel. Okay, means you have to transmit this signal over communication channel, so it must suit or match the characteristics of communication channel so that it can travel up to some distance, and that too with minimum of losses. Okay, basically we are making our signal channel compatible. All right, this chart shows you different modulation schemes. The main classification is analog type of modulation and digital type of modulation. So we'll mainly focus on analog type of modulation in here. In analog modulation, we can have three different schemes, three different classifications. One is amplitude modulation, and other scheme is angle modulation, right? And third is pulse analog modulation. Okay. Now AM can be further classified as DSBFC, means double sideband full carrier system. I mean, we are transmitting both the sidebands along with full carrier, right? Likewise, we have DSB-SC. Herein, we are transmitting suppressed carrier, right? Both the sidebands along with suppressed carrier, right? Then we have SSB, single sideband. Only one sideband is being transmitted, and obviously the carrier is suppressed. And finally, we have vestigial sideband. In vestigial sideband, we usually transmit one sideband along with vestige of another sideband, right? So we'll discuss these in detail and their generation process. Okay. Now this is the general equation of a wave, right? A periodic wave. It can be sine or cosine. Now a wave can have certain parameters, like this is the amplitude of this wave, right? This is the frequency, okay, and this parameter is representing the phase, okay. whenever we want to modulate, I mean on basis of amplitude, that becomes amplitude modulation. Whenever we change this thing, it becomes frequency modulation, and whenever we change or alter this thing, this becomes phase modulation. Okay. Now if you notice this thing, this is of the form sine theta, right, where theta is the angle, right? So if we vary any of these parameters, either omega or phi, it will become angle modulation, right? So we call this as angle modulation, and it can have two things, two classifications, FM and PM, means frequency modulation or phase modulation. Either we can vary frequency or phase, that is called as angle modulation techniques, right? Then we have pulse analog modulation techniques. It can be classified as PAM, PPM, and PWM. PAM means pulse amplitude modulation. This is pulse position modulation and pulse width modulation. If we talk about digital modulation, we can have PCM, pulse code modulation, delta modulation, and adaptive delta modulation techniques. Okay. There are more modulation techniques available, like keying modulation techniques, which covers ASK, FSK, PSK, QPSK, QAM, and many more. All right. So this was just to give a brief idea about modulation techniques. Okay. Next, we'll start amplitude modulation. Right. This block diagram, which you can see, is a modulator circuitry, and in similar way as we have seen before, there must be some low frequency signal, right, and some high frequency signal, right, which is generally generated using RF oscillator, radio frequency oscillator. Okay. This message signal is fed to this AM modulator after doing some pre-processing, which can involve amplification or filtering process. All right. And we are getting high frequency carrier from this RF oscillator. This is a generator actually. Okay. It can be crystal oscillator and anything. Okay. Now in here the wave gets mixed up, and we are going to get AM wave at this place. Okay. Then this AM is made to pass through this power amplifier, or process through this power amplifier to match the frequency of this antenna. Okay. Finally, this antenna radiates an AM wave, or you can say it is an EM wave, okay, whose amplitude is altered or varied in accordance with amplitude of message signal. Okay. Generally, this transmission can be between 550 to 1650 kilohertz. All right. So here is the proper definition of AM wave. Right. Amplitude modulation is the process in which we are changing amplitude of relatively high frequency carrier. All right. In proportion to the instantaneous value of modulating signal. Right. Instantaneous value means at this point it can be, right, instantaneous value of time. Okay. Now suppose carrier is having an amplitude of 10 volts. All right. It can be minus 10 in other direction. Okay. And let us consider the peak values of this signal to be 3 volts and this to be minus 3 volts. All right. So let's say these are the instantaneous values at suppose T1, and this is at T2. Okay. Now for positive going modulating signal, this amplitude 3 volts will get added up with this 10 volts. So this will become this here will become 13 volts. Okay. And your modulating signal, if it is going negative, and suppose we are at T2, its value is minus 3. So this minus 3 will get subtracted out from this 10 volts. All right. So we'll be getting 7 volts at this place. Okay. 7 volts. All right. Likewise, you can calculate all the intermediate values of amplitudes for this AM wave. Okay. Considering that particular instant of time. Okay. So let us try to understand this with the help of vectors and phasor diagrams. Right. This mixing of two waveforms, or modulating these two waveforms, can result in different waveforms and their harmonics. Okay. Like mainly we have DC voltage, right? Then we can have carrier at the output. Then sum of frequencies. We call it FC plus FM. FC is the frequency of carrier, right? And FM, let's say it is the frequency of message signal. Okay. Likewise, we can have difference frequencies, FC minus FM, right? and obviously we can have harmonics of these, Fc plus twice of Fm, Fc minus twice of Fm, right? Likewise Fc plus thrice of Fm, Fc minus thrice of Fm, right? Fm, sorry. But we are mainly interested in this carrier frequency and these two shifts. Okay, these two shifts basically are coming from the frequency shifting property of Fourier transform, right? As you can see in this picture, you'll notice this side is your amplitude axis and this is the frequency axis, means this is Fourier transform representation or frequency domain representation of your signal. Okay, or you can say the modulated signal, right? Now initially the message signal is at some lower frequency, the baseband signals are lying near to 0. All right, so we are making this frequency to shift to some higher frequency, that is Fc, right? So as you can see in this spectrum, we have this frequency spectrum being shifted to this frequency, and these are the sidebands of message signal, right? And we consider this Fm to be F max, right, to accommodate all the intermediate or lower frequency values of message signal. Okay, as we have seen, there are two types of shifts. One is Fc plus Fm, means this side, right? So this we call as upper sideband or upper side frequency. Okay, and another shift is Fc minus Fm, that is Fc minus Fm, shift towards this side, right? So this we call as lower sideband or lower side frequencies. Okay, and in center we have carrier, we can call it center frequency. Okay, that means Fc is my center frequency. All right, while discussing phasor diagram or vector diagram, I'll mainly consider this carrier and these two sidebands, all right, or vectors of these three. Okay, for single frequency modulating signal, like we have considered one, right, sine or cosine wave, the AM envelope is generally produced by addition of vectors of carrier, lower side frequency and upper side frequency. Like if you see in this diagram, this side it is lower side frequency, right, and this side it is upper side frequency. Okay, and this is the amplitude of carrier. Okay, or you can write it omega c. Sorry, if I'm considering omega, then let it be omega. So lower side frequency usually rotates in this direction, in clockwise direction, and upper side frequency will rotate in anti-clockwise direction, right? Now let us consider this wave as my message signal. Okay, now suppose we are at this point. Okay, so at this point there will be no amplitude, or the amplitude value of message signal is 0 volts. Okay, so at this place in here we can only have the amplitude of carrier, right? You can see, and these two sidebands will be out of phase by 180 degrees. All right, cancelling the effect of each other, right? Now suppose we are moving towards this side, means the value of amplitude is now increasing. Okay, so this sideband here will move towards clockwise direction, means lower sideband will start to move towards clockwise direction, and upper sideband will move towards anti-clockwise direction, right? And when your signal amplitude, modulating signal amplitude becomes maximum, all three sidebands, all two sidebands and the phasor of carrier or vector of carrier, they come in phase. Okay, so all the amplitudes will get added up, and this we call as Vmax, maximum voltage of amplitude modulated wave. Okay, here it is a voltage of carrier, right? Then voltage of USB, means upper sideband or upper side frequency, and voltage of lower side frequency. All right, now after this peak point, your modulating signal amplitude starts to drop, right? So these phasors will now start to move apart, right? This lower side frequency will move in clockwise direction now, right? And this upper side frequency will move in clockwise direction. Okay, and at this point when it crosses 0, your modulating signal crosses 0, so these phasors will again become out of phase, right? Means they become out of phase by 180 degrees, and the only amplitude left is the voltage of carrier, right, Vc. Then you will notice that signal will start to go negative. Okay, when it starts to move towards negative side, your phasors, means lower side frequency, will move towards this side, I mean the anti-clockwise direction, and upper side frequency will continue to move in clockwise direction. All right, and when the negative amplitude means your signal reaches maximum negative amplitude, the voltage vectors of these sidebands will get aligned, right? And this complete value means this from here to here will get subtracted out from this amplitude of carrier, right? Which is proportional to the amplitude of this modulating signal. All right. Then again, as your signal starts to rise, these phasors will start to move towards this side, right? In same manner. I mean, lower sideband will move clockwise and upper sideband will move anti-clockwise. Okay. So that is how a modulating signal makes amplitude of carrier vary, right? So that's all for now. We'll discuss or take the mathematical part in next lecture. Till then, thank you.